So good afternoon one and all. So what we are discussing here, so today we will be discussing organic chemistry. So what we discussed in the last class, tell me once. We discussed about chemical bonding. So in that we discussed about types of bonds as well as Lewis dot structure also, right? So tell me what are the limitations we have for Lewis dot structures in his explanation. So what are the rules we have studied there? So while drawing the Lewis dot structures, we need to consider the valency electrons of each element, right? So by representing those electrons as dots around the atom, okay. Now those species or those compounds are stable which gains octet rule configuration. 8 electron rules or 8 electron rule we can say are inert gas or noble gas configuration, right? Now tell me what are the limitations we have for Lewis dot structure? See, there are there are few substances which are having incomplete octet, but they are existing, they are being stable. It was not explained by him. Reason for that was not explained by Lewis, right? Again one more thing, expanded octet means few compounds are having more than 8 electrons, they are also existing. Examples, PCl5, SF6 we discussed in the last class. Then next, unable to explain the structure, like methane. What is the methane structure we are saying? Tetrahedral we are saying, but it was not given, like there is no proper explanation how it will be in a tetrahedral structure. So according to him it looks like something like this. So if this is a carbon, so 4 valence electrons of carbon we are placing like this, and hydrogen, each hydrogen 1 electron, 1s1 configuration now. So 1 electron, hydrogen 1 electron, hydrogen 1 electron. So something like this, it is looking like something like this, right? There is no proper structure explained for this molecule according to the Lewis. So this was also not given, structure of compounds are not explained. Next, noble gas configuration. Since he told that noble gas configuration species are more stable, it means they should not show reactivity, but xenon undergoing some chemical reactions, forming some compounds like xenon F2, XeF4, XeF2, XeF6, something like that. So but it should not be happen if it is really stable as per him, but it is what is the reason behind its chemical reactivity also not explained. So these are the limitations you can remember. Then next, how a ionic bond is formed? By complete transfer of electrons from cation. The electropositive element loses electron, that electron transferred to electronegative atom, right? Then next what we discussed, oxides also we discussed, basic oxide, acidic oxide, amphoteric oxides, okay. So now metal forms basic oxides, non-metal forms metalloid forms amphoteric. Generally these are general statement, okay. So now let us discuss about this organic chemistry now, okay. So what we know about organic chemistry, tell me. So first of all, most of the students will scare of organic chemistry. I don't know why, what is the reason behind that. It's very easy and interesting, okay. So once if you got that flavor of organic chemistry, you won't leave it. So it will be very easy actually, but you need to know how can we catch up that, okay. So I will try to give that kind of explanation, so try to follow the class, okay. So here I will just give you basics only. So in our actual classes, once we start the syllabus for NEET, okay, and JEE, so there I will be giving complete things about organic. Now we will look into some basic concepts of organic chemistry, okay. So now initially, so when we are studying from the basic class, what we will used to study in the books, so there are two types of compounds, organic and inorganic compounds. So organic compounds are derived from plants and animals, something like from living sources, whereas inorganic compounds are derived from like minerals, something like that, non-living sources we can say, right? Okay, so we know there is a Swedish chemist, scientist we can say, his name is Berzelius. So he told that there is something like vital force theory. It means some mysterious force is existing in plants and animals in order to synthesize or in order to produce these organic compounds. What he told, there is some mysterious force existing in plants and animals, in living things we can say, which is responsible for production of these organic compounds. But later it is proved that there is nothing like any mysterious force or vital force theory. It is, we can prepare these organic compounds from lab also, synthetically also we can do this. Okay, this was like given by later experiments. Okay, so something like we got coal base did like for production of acetic acid, then you know first organic compound synthesized in the lab is urea by Wohler. Okay, so what he taken, one inorganic compound ammonium isocyanate he taken, so upon heating, so he produced urea. So now he prepared in the lab only now. So this put all the full stops to that whatever the mysterious force, whatever the assumptions are there, so all them are collapsed. Okay, so then many different research went on. So there are many developments in organic chemistry now, right? So organic means what? It's a natural source. So at the beginning they consider it was coming only from, these compounds are coming from natural source, but later they realized that it can be produced in the laboratory also. But we are continuing with the name this organic compounds only. So now organic compounds contains, yes, who is this? L, are you sleepy? In the chat box. Yeah, so so organic compounds contains what? Mostly it will be having carbon, along with that hydrogen will be there. So now organic compounds contains carbon and hydrogen. If only these two atoms are there, we can call it as hydrocarbon. Okay, so along with this sometimes we will also be seeing oxygen, okay, and sometimes nitrogen, sulfur, and some halogens also may present like fluorine, chlorine. I am presenting with X. Okay, so now other than carbon and hydrogen, if any element is, any atom other than these two are present, we can call those organic compounds as heterocompounds. What is that? Heterocompounds. For example, you know what is this? I think you are more familiar with this thing. What is this? Benzene. Okay, sir, is this, sir, this class is fully in English? Priya, see, there is nothing like English, Hindi, Telugu, something like that. See, it is completely, I am using very basic English. Everyone can able to follow. Yes or no? So there is no point of asking it is in English or Telugu or Hindi. Priya, I hope you are following my like whatever I am teaching. I think you are getting properly only, right? So tell me, in what language you are expecting from me? See, you can write your difficult. Okay, sir. Okay, sir. Thank you. Yes. So I hope you are comfortable with my teaching. If yes, just write it in the comment box so that I will feel yes, yes, thank you. Yes, follow the class then. Okay, do not worry about what language he is communicating. Every time so many people are asking, sir, only English, why only English? I don't know what you are expecting other than that. Okay, so now this is what carbon and hydrogen we have in this compound. Now what I am doing is, see, out of this benzene, one carbon I am replacing with one nitrogen like this. So what we have here? Nitrogen. So we should call it as benzene, and this is benzene, this is pyridine. What is the name of this compound? Pyridine. So in pyridine we have one nitrogen atom here. So can I say this as heterocyclic compound? Both are cyclic compounds. This is completely carbon and hydrogen only. In this we have one hetero atom. So can we call it as heterocyclic compound? Yes. So whenever we have other atoms other than this carbon and hydrogen, we should call them as hetero compound. If it is in cyclic manner, heterocyclic compounds. Is that clear? Yes. Next, once read this. let us study, see, since we know in organic compounds we have majorly carbon, right? So we need to discuss little more about carbon so that we can understand the chemical reactions shown by the carbon very easily in this organic chemistry. Okay, so carbon exhibits valency 4. What is the valency of carbon? This is the maximum valency shown by the carbon. So why we are saying it as 4 only? Just atomic number, tell me carbon atomic number 6. So you can write electronic configuration 1s2, 2s2, 2p2. Okay. Now what is the valency electronic configuration? Here we have Priya, because I am come from Tamil Nadu. See Priya, you know I am also from Tamil Nadu. I mean I am from Telangana only, but I studied in Tamil Nadu from Pondicherry. Most channels are teach in Hindi or English, sir, not in. So that's why I ask you. See, Priya, so here we will definitely provide you quality content, but it is in English majorly. Okay. So I think Tamil people are more familiar with English rather than any other language after their Tamil, right? So I hope this channel will definitely give you and help you most than any other channel. So you can follow this properly and regularly. And you know our physics faculty is also from Tamil Nadu. I mean he knows Tamil very well than me. Yeah. Yes. So my name is Ajay, you can see in the description box, right? Yeah, fine. So we have, this is the electronic configuration we know. Now these two, this is what the valency electronic configuration we are saying now. Why we are saying, see, this is 1s, this is 2s, which is having more energy as number of this principal quantum number we used to study. It means this n value, this number is there now. So highest number is 2, right, for this electronic configuration. So we can say this is the highest energy level. So where we have 2s and 2p orbitals. So this is the valency electronic configuration. So only these valency electrons will involving in the chemical reactions. Okay. So now how many electrons are there in s orbital? This is 2s. I am writing 2 electrons. Again 2p. I am writing like this. Is there any confusion in this? Now totally how many electrons are there we have in the valency? 4 electrons. How many orbitals we have in the valency? Orbitals. See, this is one orbital, one box is one orbital you can consider. This is one orbital, second, third, fourth. So total 4 orbitals are there. Now after excitation of electron from here to here, so now what we are getting? We have 4 orbitals like this. 1, 2, 3, 4, right? 4 orbitals are there. Okay. So now one electron in each orbital now. So let us say, let us understand the formation of methane so that it will be more useful, easier to understand here. Okay. Now this is about carbon. This is about what? Carbon. Now hydrogen electronic configuration, you tell me. Atomic number is 1. So I can write 1s1. It means hydrogen is also having only 1 electron in their valency. Now in order to fulfill this hydrogen electronic configuration, it means in order to get helium gas configuration, right? So we required 1 more electron so that it will become 1s2. Similarly, in order to get nearest noble gas configuration for carbon, how many electrons are required in order to fulfill these orbitals? 1 electron is there now, still 1 more electron is required in each of these orbitals. So total 4 electrons are required. So how many electrons are required for carbon? 4. So it means hydrogen required 1 electron, carbon required 4 electrons. Therefore each of this electron of carbon can overlap with the hydrogen orbital of 1 electron, so that it will becoming 2 electrons. So here also 1, here also 1, here also 1. So now 1 electron from carbon, 1 electron from hydrogen. So that totally how many electrons it is becoming with the carbon now? See, this white color electron represents it is from hydrogen. So totally carbon becoming octet configuration now. 8 electrons are fulfilled now. So all the orbitals are fully filled, right? So it means now after forming methane, now this carbon is getting stabilized. right? Similarly, hydrogen also, this electron from carbon, this white color electron from hydrogen. So each hydrogen is also getting 2 electrons in a helium gas configuration. Like that you can understand. Okay. So now what is the maximum number of electrons required for carbon in order to fulfill its octet? 4. So maximum number of bonds formed by carbon is how many? Maximum, see, it has 4 orbitals only, so it can form only maximum of 4 bonds. More than that, not possible. Clear now? Yes. Even now tell me, just go with nitrogen. Tell me how many bonds it can form maximum. So simply you can write the electronic configuration of nitrogen. Nitrogen you can write. So after doing this, tell me what is the valence electronic configuration? 2s2, 2p3. So just represent it like this. 1, 2, 3, 4, 5, like this. Okay. Now how many electrons nitrogen is also containing? How many, like see, unpaired electrons, how many are there? 3 unpaired electrons are there. Total how many orbitals it is having? Valency orbitals? 4. So nitrogen also having 4 valency orbitals now. It means it can also form maximum of 4 bonds only. It cannot form 5 bonds. Is that clear? Yeah. So just count number of orbitals in the valency, that many bonds it can form. In the case of nitrogen and carbon, both it is same. Hope it is clear. Now let us discuss little more about carbon. So we can call it as tetravalency of carbon, right? Next, what are the allotropes of carbon? So we have 3 allotropes. One is diamond, graphite, fullerene. Okay. So each carbon in diamond will be sp3 hybridized. So each carbon is how much? What is the hybridization? sp3, and it will be having 3-dimensional shape. Okay. So now it is the hardest natural substance known. Okay. Now graphite we use in our pencil lids. Okay. It is having hexagonal layers. Okay. It is very smoothy and slippery, therefore it is used as a lubricant. How can we use? Yes, lubricant. So lubricant in the means, I mean in bearings, in heavy industrial purpose it will be used. So how it will be acting as lubricants? See what they mentioned, hexagonal layers na. So there will be layers like structure. Let us say something like this, it will be layered structure will be there, top one layer, bottom one layer. So between them there will be slight interactions are there. So due to the slight interactions, see here like pi electrons will be there. So by the top layer and bottom layer there will be some interactions are there. So due to that interactions it will be like slippery, it will be giving its slippery nature, so that it will be used as a lubricant. Greasy feel we can get when we touch the pencil also will feel greasy, right? Yeah. Then next, fullerenes are example. Here I have mentioned C60. So if you see football structure, football you know now, so how it will be? Something like it will be having some hexagons. If you look into the ball properly, it will be having some hexagons. Okay, like that pentagons also there. So they will be condensed form. Okay, so it will be having 60 carbons, so C60 we can say, or sometimes C70 will be there, C80 will be there, like this. So it will be having football shaped. Okay, we can also call them as Bucky balls or Buckminster fullerene we can say. Okay, so now these are used in the cancer therapy. What is it? Okay, and there are many other applications also for these fullerenes. Like nanotubes, they will be used in the nanotube applications. Okay, now tell me an allotrope of carbon which is hardest one? Diamond. Okay, allotrope used as a lubricant? Graphite. So what is mean by catenation property? What do we mean by catenation? Yes, are you there? Yes in the chat box. Yes, tell me what do we mean by catenation? See, it is a unique ability of carbon. See, carbon will be there, na? Carbon atoms will be there. Na? It is a self-linkage property of carbon. It means carbon can link with other carbon atoms. It means the self linkage property we can say. Okay, so carbon having unique ability to form a carbon long chain we can get like this. Okay, each other, and it can form a rings by joining carbons we can get a long hydrocarbon chain, or we can get a ring also. Okay, this property give rise to alkanes, alkenes, alkynes and aromatic compounds. Okay, so what exactly alkenes, alkanes I will show you now. Okay, so what do we mean by catenation? It is a self linkage property of carbon. Okay, next. Okay, so now here what we hear, after by this property we have organic compounds like carbon compounds like alkanes, alkenes, alkynes and also hydrocarbons. Now let us say these carbon containing compounds will be segregating into two types. One is saturated, another one is unsaturated. Okay, one is saturated, another one is unsaturated. So let us study about saturated and unsaturated compounds. Okay, so saturated compound means between carbon and carbon we will be having only sigma bonds, only single bonds we have. Okay, what I am saying, saturated compounds, only single bonds between carbon atoms. See, between carbon and carbon, whatever the longest it is, how much long it is, no issues, but it will be having only sigma bond, only single bond between two carbon atoms, whether it can be in the cyclic form or it can be in the open chain like this. It will be having only single bonds between the carbon atoms. Is that clear? So those compounds are called as alkanes. If it is a straight chain like this, we can say alkanes. If it is cyclic like this, we can say cycloalkanes. What is that? So in alkanes, each carbon is hybridized is sp3. What is the hybridization of each carbon? sp3. Okay. Next, what about unsaturated compounds? Contain one or more double, triple bonds. Example, alkenes and alkynes. It means, for example, carbon-carbon linkage will be there like this. So between carbon-carbon there will be at least one multiple bond. I mean, at least at one position between two carbons there will be at least one pi bond in the given compound. We can consider it as saturated or unsaturated? Unsaturated. Now, what is the hybridization of each carbon here we have? sp2. When we have one double bond between carbon-carbon, we can say sp2. Sometimes there will be two pi bonds. See, one sigma bond and these two you can consider it as pi bonds, two pi bonds. So what is the hybridization of each carbon here? See, while drawing the structures, the valency of carbon should be satisfied in all the cases. It means, here I have mentioned carbon-carbon bonds. It means, see, this side one bond, this side another bond we have mentioned. So till it can form two more bonds now. So now you have to write one hydrogen here and one hydrogen here, so that carbon valencies is satisfied in this case. So like that you should apply that concept in each of the case while writing the structures. Now here you tell me how many bonds it is forming. Already two bonds this side. So this side again we can place two hydrogens. Now what about this carbon? 3 bonds over, so we can place one hydrogen. 4 bonds should be there around the carbon. This side we can place like this now. Yeah. So now these two carbons are sp2. Now what about these two carbons? Yes, sp hybridized. So how many, like see, these are 3 bonds. This 4th bond should be attached with some other atoms like hydrogen, carbon or anything, but its valency has to be satisfied. Hope it is clear. Next. So these are alkenes, these are alkynes. Okay. Now these compounds can be in the cyclic form also. So now tell me, is it saturated or unsaturated? Saturated, alkane, right? Now, is it alkene or alkyne? Alkene. Now tell me, what is the name of this compound? Cyclo. So we can say alkane. Now how many carbons are there? See, each of this indicates what? carbon atom. So like that, how many are there here? 5. So cyclo, 5 means we have 5 carbons, means we can say pent. So cyclopentane we can say. Okay. So now here I am writing a double bond. So whenever we have one double bond, we are saying it as alkene, right? Alkene. So this what you need to use. So cyclopentene. What is that? Cyclopentene. Okay. Now here when we have triple bond, we are saying it as alkyne. Alkyne we are saying na. So name should be end with yne, ine. So if we have multiple triple bond like this, so multiple bonds, so what I can say? Cyclopentene, something like this. Is that clear? Yeah. So for this we can write cyclopentene. Okay. So about IUPAC we will be studying in the upcoming classes. Now let us see few more basics of this thing. Okay. So how we classified organic compounds? Saturated, unsaturated. See, there is nothing like cyclopent 2 in 1 in here. See, because there is there is nothing to specify the numbers now. See, wherever you have functional group, there only you have to write the number 1. Okay. So 1, 2, 3, 4, 5. So it means at the first carbon only we have double bond now. So it means cyclopent 1 in you can say, or simply cyclopent in you can write. There is nothing to specify cyclopent 2 in. Priya in the comment box. It is wrong ma. Next tell me, hydrocarbons. These are compounds made up of only carbon and hydrogen. Now we have seen saturated compounds that are alkanes. So these are unsaturated. So now what is the general formula of alkanes? CnH2n plus 2. For example, n equals to 2 means C2H6. C2H2, 2 to the 4 plus 2, 6. So what we should call 2 carbons are there means ethane. What is that? Right now? What about this? Tell me what about that? CnH2n is alkene. So we have C2H4. This is ethene. Simplest alkene is what? Simplest alkene possible is what? Ethene. See, simplest alkane if they ask, you can say methane, but simplest alkene is ethene. And now what about this? CnH2n plus H2n minus 2 means C2H2. So it is ethyne. So its structure will be looks like this. Here what is the hybridization of each carbon in this case? 4 sigma bonds are there now, so sp3. So in this case CC double bond H, okay, and next so both are sp2. What about here? C triple bond C H. Just count number of sigma bonds in this. See, this is 1 sigma, second sigma for this carbon I am saying. This is again third sigma. So 3 sigma bonds now, S1, sp2, sp1, p2. So what we are getting here? sp2. This side also 1 sigma, second sigma, third sigma. So both are getting sp2, sp2 only. Now what about this? How many sigma bonds are there? Here 1 and here 1. 2 sigmas only. So here also. Clear now? So number of sigma bonds gives its hybridization number. Number of sigma bonds plus number of lone pair electrons gives its hybridization number. Okay. Now what about hydrocarbons? What about hydrocarbons? Aromatic hydrocarbons. Aromatic means what? It's a special type of compounds in organic chemistry. So they should be generally cyclic, okay, and it should be having unsaturation on each carbon, okay. So the simplest aromatic hydrocarbon we know is benzene, okay. Compounds with benzene and its derivatives, benzene rings, example benzene and toluene. So toluene means benzene ring with methyl group, this is toluene. So these both are aromatic. So about aromaticity definitely we need to study, because we can expect a question from this, okay. Next, what about functional groups? So functional group means it is an atom or group of atoms which describes the chemical property of that particular compound. If I give one organic compound, so its properties, its chemical properties is described by a set of atoms, a group of atoms or a single atom that can be considered to be the functional group of that particular molecule, okay. Atom or a group of atoms describes the chemical property of that particular organic compound are considered to be functional group. For example, here I am writing CH3 CH3. What is this? Just a alkane, ethane we can say. So now from this what I am doing is I am removing one hydrogen from here. See what is the valency for this carbon now? 1 bond, 2, 3 bonds only. But what is the valency it should have? So now that fourth valency I am placing with one OH group. Now it is becoming alcohol. What is that? Whenever we are adding OH, it becomes alcohol. So now it will be having a special properties, okay. That is characterized by what? This OH group only na. Initially what you have seen? CH3 CH3, this simple ethane. Now it is completely converted into some special category, right. Now it will be having some special properties when we compare with this, right. That is due to presence of this OH. Now this OH group is considered to be the functional group in this molecule. Is that clear? Like that we have alcohol functional group, aldehyde, ketone, carboxylic acid, amine and halides, okay. So this is about basic understanding of functional groups, okay. Now see carboxylic acids, the name itself saying it will be having acidic nature. What is that? So like citric acid we are saying, or acetic acid we are saying, or formic acid. So these are all comes under the examples for this carboxylic acids, okay. Now what about amines? So these are basic in nature. So they will show basic nature in the organic compounds or chemical reactions, okay. So we will discuss about that later. Next, now organic compounds, see they will be having same molecular formula but they exist in different structures. So read once. Isomers means what? Isomers are compounds with the same molecular formula but different structure. If they are different in their structure, those isomers are called structural isomers. So what do we mean by isomers? Compounds with the same molecular formula. If they are different in their structure, we should call them as structural isomers. If they are different in the spatial arrangement of atoms, what do we mean by spatial arrangement? In this 3-dimensional space, the arrangement of atoms are differ. Then we can call them as stereoisomers. So what are the isomers we have? Two types. One is structural, other one is stereo, right? So structural means differ in their structure, stereo means differ in spatial arrangement of atoms or group of atoms, okay. So now let us discuss about structural isomerism to some extent, okay. So now these structural isomers are chain isomers, positional isomers, functional isomers. Like this we have different classification here. So let us understand the basic idea on this structural isomer. So tell me what is the name of this compound? I hope you know how can we write the names of organic compounds. What is the name of this compound? Butane. So now I am placing one alcohol group over here. Now tell me, Bansali Good afternoon. In the chat box. Yeah. So what is this? Alcohol. So we can say butanol. What is it? So here we have the alcohol group now. So I am giving number 1, 2, 3, 4. So can I say 1 butanol? Okay. Now same I am writing same thing, same butane I am writing, but I am placing OH group at this position. Now do they have same molecular formula or not? Same number of carbon atoms, all carbons are sp3 hybridized, there is no multiple bond, pi bonds are not there here and there, so molecular formula definitely same, but position of OH group is here 1, there it is 2. So can I write it as 2 butanol? So what is the difference between these two? What is the difference between the two? Position of functional group. See, position of OH is 1, here position of OH is 2. So we can call them as these two molecules are, two compounds are isomers, okay, and they differ in the position of functional group. So can I say positional isomers? Yes. So both are what now? Positional isomers. Positional isomers. Now with the same molecular formula I will be creating one other compound. Let us see here. How many carbons are there? 4. So I am writing here CH3 with 4 carbons only I am doing CH2 O CH2 CH3. How many carbons are there here? Here how many are there? Oxygens how many? Here also 1. So do they have same molecular formula? Yes, molecular formula is same, but they differ in the functional group. What is the functional group? Here we have alcohol, so we are saying them as butanol, like that. So these are like ROR bond is there, means alkyl group, carbon atom, oxygen, again carbon atom if we have like this manner. So we can call them as ethers. What is it? Ethers. Okay. So this is, now it is ether, diethyl ether we can say. What is that? See, this side one ethyl group, this side another ethyl group. So diethyl ether we can call it. Okay. So now one is butanol, one is alcohol, another one is ether. Both are different functional groups now. So compounds having same molecular formula, but they differ in their functional group. So we can call them as functional group isomers. What is that? Functional group FGI I am writing. What do we mean by that? Functional group isomers. I hope it is clear. Yeah. So like this we have chain isomers, functional isomers, next positional isomers. If they differ in the chain we should call them as isomers which differ in their chain isomer, differ in the positional isomer, differ in the functional group. About tautomerism we will study in the upcoming classes, not now. Next, stereoisomerism. Here also I will give you some basic idea about the stereoisomers, okay, so that when we are discussing it properly, then that case you won't feel it is new to you. Okay, look at here. I have carbon-carbon bond, like double bond. What is the hybridization of each of these carbons? sp2. If it is sp2 hybridization, we know it will be having square plane or like what is it? Trigonal planar geometry, right? So I am saying planarity na, trigonal planar I am saying. It means molecule will be, this is planar, this is also planar. Both are in plane only now. So can I say molecule is planar molecule now? Yes, molecule is planar. Now I am taking element A here, some substance group A is there attached to this, and here B is there, here also A is there, here one B is there. Okay. Now same compound I am writing here. Now tell me, how do these two are differ? What is the difference between this compound 1 and compound 2? How do these are differ from each other? Yeah, carbon carbon, here also carbon carbon double bond is there. See, on this carbon we have AB, on this carbon also AB. Okay, here also AB, like that only we have. But you just check the position of this A with respect to the other atom. Here also it will be having A. So on the same side of this double bond, see, on different two carbons we have same groups now. So when we have like this, we should call them as cis. What is that? Cis. Now here you can see A and A, here they are at 180 degrees to each other, opposite side now. So whenever we have in the opposite direction like this, we can call it as trans. Now one more thing you need to observe. So these cis trans isomers are called stereoisomers. Up to here it is clear now. Now let us consider Sanu. Who is that? Yes, you are really active person, man. Yeah. So now here we need to compare this stereoisomer to structural isomer so that it will give us more clarity. In the structural isomerism, if you compare, what is the position of OH? 1, here it is 2. It means bond connectivity is different now. See, OH group is connected to first position, in this it is connected to, so bond connectivity is varying here. But when it comes to stereoisomers, bond connectivity remains the same. See, here AB attached to the same carbon, here also AB attached to the same carbon, but spatial arrangement is different. Are you following that statement? How do they differ? In the three-dimensional space, the position, the spatial arrangement of atoms are varying here. Yes or no? So now isomers which are differ in the spatial arrangement of atoms is called stereoisomers. So A1 and 2 are called stereoisomers. Is that clear or not? Yeah. No confusions now? Yeah. Yeah. Then next, one more thing also I will tell you. See, in the definition I have mentioned something like geometrical isomers, cis trans. This is what cis trans or geometrical we can say. One more, what is there? Here we have optical. So what do we mean by optical isomerism? I will tell you. Here also I will give you some basic idea, but little more clearly. See, I am writing carbon. So carbon, what is the maximum valency of carbon? 4. Okay. So it means 4 bonds I can place on this carbon. Like this I am placing. Okay. So on one carbon, let me write this as this indication is what? So this bond is towards the observer. If I am looking at this molecule, so this bond is something like this. If this is the plane, on the plane we have one carbon, to that carbon we have one bond like this. See, this is towards the observer. No? So here whatever atom I am writing, let us say here I am writing atom A. So this atom is towards observer. Okay. Now one bond I am representing here, this bond, let us say with something like this. I am writing B. So what it is indicating? This bond is away from you or below the plane I can say. It means if this is a plane, so this bond is back side of this board. Is that clear? So something like this. This black pen is towards you and this index finger is away from you, that is below the plane I can say. Now I am writing 2 more atoms. Here I am writing hydrogen, let us say, and here I am putting one element D. Okay, like this we have. So now to the carbon, 4 different groups are there now. See, what is the maximum valency of carbon? 4. So this maximum valency, the 4 groups are different groups. Okay. Now I am taking a mirror image of it. Observe, let us consider here we have mirror. Okay. So this is a carbon, again I am writing. See, as it is D I am writing here. See, now what happens? If this is a mirror, this above the plane will become below the plane becomes above the plane in the mirror. Do you know or not? So if you look into the mirror, so something like this, if we are putting, that will looks away, it means opposite side will be feeling. So here I am writing here, what I should write on this, I should write mirror image, I mean below the plane becomes above the plane, like that I am saying now. So it will becomes what, here I am writing B, I am writing, why I am writing B here, below the plane becomes above the plane, I am saying now, like that, okay. And here it will becomes A, and one more we have hydrogen, I am writing as it is hydrogen, okay. So now these two, how do they differ from each other? So they are mirror images, I am saying, just take one molecule, its mirror images will look like this. Now see, there is something called optical isomerism. It means we have something called plane polarized light. What I am saying? Plane polarized light. So when I am sending the plane polarized light through this solution, if this compound is A compound, let us say, okay, to this solution, if I am sending that light will be rotated either rightwise or clockwise or anti-clockwise. Okay, if it is rotating clockwise or anti-clockwise, we have one isomer called R isomer and S isomer. If it is, for example, let us say it is rotating clockwise, let us say I am considering that isomer as R. Now its mirror image is there now, so that will rotate that plane polarized light opposite direction. It is rotating right side, then it will rotate left, I mean anti-clockwise. So that isomer is called S isomer. If it is R, that will becomes S. Okay. So now how do they differ? They are differ in the rotation of that plane polarized light. Molecules look same. These are also considered stereoisomers only. See, same bond connectivity is there now, but spatial arrangement of this AB is varying here and there. Yes or no? So now these isomers are called stereoisomers, and specifically we can say optical isomers, because their optical rotation is different. It is rotating clockwise, it is rotating anti-clockwise. About this optical activity we will study later, but what I am saying, there will be R isomer, other one is S isomer, their optical rotation is completely opposite to each other. You can remember up to here. Now these two isomers are called enantiomers. What I am saying again? About this terminology also we will study later. Just I am just giving you that inputs. The terminology you should not feel new when you hear them later. Okay, then next. So when it comes to IUPAC nomenclature, okay, so what we have here? So IUPAC nomenclature, rules to name the organic compounds is given by this IUPAC. So what is that? First one is identify the longest carbon chain. Okay, so parent chain, we are saying that longest carbon chain is a parent chain. Next, number the chain from the nearest substituent. For example, here we have like this, here we have like this, okay, and I am having like this, Now tell me, what is the name of this molecule? Identify the longest hydrocarbon chain. See, if I give numbering from here, 1, 2, 3, 4, it will be 4 member. So if I start from here, 1, 2, 3, so which is bigger number, first case or second case? First case. So giving in the first case manner is good, like this. So should I give from here or from here? So if I give numbering from here, 1, 2, 3, 4, yes, which one is correct? Yellow color one or white color one? Yellow color one is correct. Why yellow color one? Second rule you can see, number the chain from nearest substituent. Nearest substituent is from here. So what is the name of the compound now? It will become 4 carbons are there. So here I have a table. Yeah, 1 carbon is, if we have, we are calling it as myth. If the parent chain having 1 carbon, we can call it as myth. 2 carbons, ith. 3, 4, 5, 6, 7, 8, 9, 10, 11, undec, 12, dodec, 13, tridec, like that. Okay, 14, tetradec, like that. Now here how many are there? 4 means but. So but is fine, but where do we have the substituent? Name and substituents. Name. So what is the name of the substituent then? How many carbons are there in the substituent? See, this side one line is there. It means here this terminal represents one carbon. Okay. So can I say methyl? One carbon means what? One carbon means what? Meth. So it is a substituent now. So we should call methyl. What is the position of this methyl? 2 methyl. First letter is capital. 2 methyl butane. Okay. Use suffixes and prefixes to indicate the functional groups. Okay. Next, what about this chain? You tell me. What is the name of that compound? Second one. 2-ethyl. 2-ethyl. This is how people do wrongs, errors. Tell me. What I told you, what is the first rule? Identify the longest chain. I am not saying identify the straight chain. I am saying identify the longest chain. Which is longest chain? From here if I consider, here 1, 2, 3, if I go this side it will become 4 only. If I come this side 4, 5. So which is bigger chain? 5. So this side is bigger, 5. So I can consider this carbon as substituent. What is the position of substituent? Even if I come from here it is 3 only, here also 3 only. Yes. So we can say 3-methyl. Yes, 3-methyl. Next, pent. That's it. Clear now? Yeah. So few more. For that, tell me, for this you tell me first. So today just I am giving you some basic idea. Tomorrow, in the next session, we will be discuss particularly only on this IUPAC nomenclature. Yes, tell me. Cyclo. We have a methyl group. This is cyclic ring. What is the number? How many carbons are there in the chain? Cyclic ring, 5-membered ring. Okay. So 5-membered ring means pent. So can I say methyl cyclopentane. Okay. Methyl cyclopentane. Now what about this? Butene or 1-butene, but-1-ene you can say. Okay. Next, when we have single bond between carbons, we are calling it as 2 pi bond, 1 pi bond, 1 sigma bond. That is what double bond. Ene, triple bond, ine. Suffix means, you know now in grammar we will use prefix, suffix, those things. Suffix means at the end, prefix beginning. Okay. So now functional groups, suffix and prefix with respect to them. So halogens we have means, if we have fluorine we should say fluoro. Always use them as prefix only. So if we have something like this, I should say that as 2-fluoro-butane. Okay. Now here I am having chlorine. Tell me. Fast. F comes first or C comes first? So C, right? So 2-chloro, 3-fluoro-butane. Follow alphabetical order here. Clear na? So halogens always prefixes. Okay. Next, alcohol. if we are using it as suffix, you should say ol. If we are using it as prefix, you should say hydroxy. What is that? So when to use prefix and suffix? For example, here in the given compound, here we have chlorine, here we have ol, OH. Now OH is more priority functional group here, so I will tell you the priority of functional groups also. But now tell me, I am saying OH is priority functional group now, so this is a principal functional group. Okay, so now if I say 1, 2, 3, so what is the name of this? 2-chloro. So when I am saying this priority or functional group, or it is a principal functional group, name of this functional group end should be end of this name. I mean, it should be the suffix. So what I can write? 2-chloro prop pen ol. That's it. Okay. Now we have aldehyde. Suffix should be al. Like instead of here we have OH. If we have CHO group, aldehyde group. So 1, 2, 3, 4. 4 carbons are there, na? Now tell me, what is the name? 3-chloro butanol. What is that? Butanol. Butanal. Butanol. Like that. Okay. So if it is sometimes it can be also prefix. That case we can get aldo or farmyl. What is the name? Prefix of aldehyde is aldo or farmyl. Similarly for ketone, prefix is keto or oxo depending upon the condition. Suffix is on, keto like pentanone, butanone, like that. Carboxylic acid, suffix is oic acid. Generally prefix we will be seeing as carboxy. Yeah. So this is about the IUPAC nomenclature. Okay. So now remaining things means the real applications of IUPAC proper. Let us take few more examples in the next class, and we will study all the IUPAC nomenclature part. Okay. So I hope everything is clear. If you have any doubts, you can ask me now. Any doubts? No doubts. Okay. Yes. So online students, I mean live session students, if you have any doubts, you can write in the comment box. Yes. So if no doubts, I will be ending of the session.